So in the previous session we have seen the problems on subspace, the column space, null space and basis, and also we have seen the basis and dimensions. So now we'll means today we'll see about the dimensions of the subspaces, so different subspaces, the dimensions and rank and nullity. Okay, so here before that just we'll revise some of the problems on the column space and the null space here. Okay, so now, so which is required in the fundamental subspaces. So now, in this problem, so we need to find out the column space, null space for the given matrix here. Okay, so in this matrix, so this is nothing but the b term. Okay, this is the a factor. Okay, and here it is nothing but like x. Okay, u v w. So here, so whatever these vectors, the matrix, okay, the columns what we are seeing, okay, these columns we can take as the v1, v2 and v3. Okay, these columns you can take as v1, v2, v3. The same thing they are taking as means x1, x2, x3. Okay, maybe the notation may be the change. Okay, so like whatever c1, x1, c2, x2 and c3, x3, or we can call as alpha v1, alpha v2, alpha 3. Okay, so here in this problem we have taken as alpha x1, alpha x2 and alpha x3. So whatever the columns we are seeing of the columns with respect to matrix, so what we are seeing, so each column, okay, this each column we are calling as the basically what is a column space. So column space is nothing but the linear combination of the columns of the matrix here. Okay, so here the whatever the columns of matrix, okay, this we call as the column space. Okay, the same, that is alpha x1 plus alpha x2 plus alpha x3. So that I am writing as alpha x1 means that first vector, x2 means second vector and x3 means the third vector. Okay, and the same thing if I write in the equation, the same matrix, if I write in the equation means alpha 1 plus alpha 3 means the first one, the third one, and the next equation, that is 5 alpha 1 and 4 alpha 2 and 9 alpha 3. Okay, so here, so the same, the matrix we are representing in the column spaces here. Okay, the representation like this of a matrix we call as the column space of A. Okay, similarly if you come to the null space, so null space is nothing but Ax equal to 0. Okay, so we need to solve the Ax equal to 0. Yeah, so A already he has in the problem it is given. Okay, now the next, okay, take the matrix. So we can as a augmented matrix, okay, so as a augmented matrix we can include either 0 0 0 means Ax equal to 0, we can make as 0 into matrix, otherwise we can leave as it we are considering as 0 0 0. Okay, apply the row operations method. So finally we are getting this the matrix now. Okay, after the reduction. So now in this case the third variable is free variable here. Okay, because if you take the 0 means b vector, okay, the b vector is 0, so it is null space we are considering b vector is 0. Okay, if b vector is 0, if we equate here, the third variable is free variable because it is mapping to 0. So system has the solutions now. Okay, it's not like system has no solution, system has a solution. So now if you write the equation, means we are taking the vector as u v w. Okay, as we have seen earlier, u v w. So the expression what we can row reduced form, u plus w is equal to 0 and v plus w is equal to 0. So if it is like that, then it will be expression u is equal to minus w and v is equal to minus w. Okay, so as third variable is free variable, so we can assume w is equal to 1. If we assume w is equal to 1, the vector is like this. If the w value is minus 1, the vector is like this. So any one we can call as the null space here. Okay, null space is equal to alpha of, so one of the vector. Okay, so if you use that one, so then it will means it will satisfy the Ax equal to 0. Okay, so this is how the find out of the null space and also the column space what you have seen previously. Okay, so now the next problem we will move on. If 1 3 4 is in null A, sorry 1 3 minus 4 is null A, where A is equal to this one. Okay, means we need to determine, is it, if the value is x is 1 3 minus 4, will it become null A? Means what we need to do is we need to just see that whether ax equal to 0 will get. Okay, so this is A and this is it, can we get 0? So that we need to verify. Okay, again apply the row. Okay, so here, so sorry, it is not, sorry, so here it is not the row application here, just it is a multiplication A into x. Okay, so after multiplying A into x, whether we need to get 0 or not, we need to check. So after doing the multiplication, okay, so you'll get this value. So finally we are getting the 0 vector, means A into x. So we say that 1 3 and minus 4 is it is in null A. Okay, so similarly the previously what we have seen some problems, the same problems, just it is like the revision here. So means the same problems asking in a different ways. Determine whether the given set of vectors span the vector space. Okay, is it these are whether the span of the given vector space. Okay, in first case r is equal to 3. Okay, first is called r, means n is the number of elements in vector is 3. There are 3 vectors here. The same vectors we can take in the matrix form, equation form, vector equation, that is 7 into the same vector we are writing in vertically 1 minus 1 2 1 1 2 0 0 1, and here we need to find the span. Okay, we need to find the span, means we need to take, it is nothing but basis also, we can call as find out the basis. In that case we need to take a b. Okay, either we can take as b1 b2 b3 or xyz, anything we can take. Okay, just to equate to any 3 unknown variables. Okay, xyz we have taken. Similarly we have written the equation, means first one x1 c1 c2, as c3 is 0, c1 c2 is equal to x, so minus c1 plus c2 is equal to y, and 2 c1 plus 2 c2 plus c3. Okay, so we have written equation. So after that then so we need to do the row operation. For the row operation, so these b also it will go under, means as a matrix now, as it is augmented matrix. Okay, so by doing that these two operations we will get these equations. So finally the c is equal to, directly we can say z is equal to minus 2x. Okay, this c3 we can substitute in the second equation, and that one we can substitute in the first equation. So finally through the back substitution we can find out the values of c1 c2 and c3. Okay, so if it is matching, okay, if it is matching with, means if we do again the cross multiplication, if we are getting as xyz, then this we call as a, means these vectors are the span of the given vector space. Okay, so what we did here, okay, we have taken, means as the matrix has given. Okay, so matrix is, means the vectors has given, you take unknown value as b, x1 x2 x3 or xyz, whatever it is. Okay, then you take augmented matrix and do row operations and find out the values of c1 c2 c3. Okay, similarly the second problem, that is 1 minus x comma 3 minus x square, and third one is x. Okay, the same thing, either here the method is different here. So we are equating the c1 into v1, c2 into v2 plus c3 into v3 is equal to through the polynomial. Okay, so whatever the equation we are equated to, like similarly like a0 plus a1x plus a2x polynomial. Okay, so the same thing, cross multiplication we have done. After the cross multiplication, and what are the variables, means c1 c2 with respect to the position, means for the x square we have minus c2, for x position we have c3 minus c1, for constant we have 3c2 plus c1. Okay, then we have equated to the particular thing, means 3c2 plus c1 is equal to a0, and C3 minus C1 is equal to A1 and minus C2 is equal to A2. Okay, so by solving these equations we will get the values of C1, C2, C3. Otherwise the same problem means the 1 minus x and 3 minus x square and x, similarly we can write in vector form also. Okay, for example x square x and constant means you can write x square x and whatever constant is there. Okay, in that case the three vertical means the three elements, okay, in vertical, so we can write in matrix v1 v2 v3. So that problem also we can do, or we can do in this method also, anyone is possible. Okay, the third one similarly, that's why I told we need to find out c1 c2 c3, and hence so this spans the whatever polynomial equation here. Okay, the next one, so first one is directly vectors, second one is polynomial, third one they have given as a the matrices here, square matrices, 2 is to means 2 is to 2, 2 cross 2, the square matrices. In this case the basis means to show that the span we need to consider again same similar size 2 to 2 matrix, the variable. Okay, we can take as sorry x1 x2 x3 x4 or abcd. So we have taken as abcd here. The similar, the same thing we can write in the equation and form the matrix here. Okay, like we can see here 2 1s, the first matrix if you see the 2 1 0 0, second one 0 0 2 1, and the third matrix 3 1 0 0, and the fourth one 0 0 3 1. Okay, so the each matrix is nothing but the one column here. Okay, then apply the row operations. Okay, apply the row operations, and which will apply to the whatever abcd, the unknowns, for that also it will apply. Then we need to equate. Okay, then we need to equate because the minus one, so last one, okay, that is c4 is equal to, directly we can take as c minus 2d. Then you need to do the back substitution. Okay, substitute for c2, substitute for c1, so like that. If you do the back substitution we will get c2 value, c3 value, c4 and c1 value. Okay, so hence as we got the values with respect to the variables, then we say that given matrices span the subspace, sorry, vector space. Okay, then the next one. Okay, here so earlier we have seen the problem with vectors, polynomials and matrices, and here some of the equations they have given means let V be the vector space. Okay, V is a vector space here. Suppose u1 u2 u3 span V. Okay, suppose u1 u2 u3 span V. In that case where u1 is, okay, so v1 is equal to u1, v2 is equal to u2 minus 1, v3 is equal to u3. Prove that. Okay, so what he says is, he says u1 u2 u3 are, it spans the V, but the vectors containing u1 u2 u3, okay, u1 u2 u3, that is v1 v2 v3, whether is it span the V, so that we need to prove. Okay, so here, so what we need to do, so we know that vector equation means the V is equal to c1 u1 c2 u2 and c3 u3. Okay, so here v1 is equal to u1, so whatever they have given, v2 is equal to u2 minus 1 and v3 is equal to u3. Okay, so let's do, okay, so let's do this one. What is this? The vector addition. So here as we know un is equal to v1, keeps that same it is, but here the second equation we have v2 is equal to u2 minus u1. So wherever u1 is there we need to replace v1. So if you replace v1 here, then it will be u2 is equal to, the u1 will come this side, so it will be v2 plus v1. Okay, so u2 is equal to v2 plus v1 and u3 is equal to v3. Okay, if you, the same thing if you apply in this equation, the c1 v1 plus v2 plus v1 c2 and c3 into v3. Okay, so now if you take the wherever the common things are there, means the c1 plus c2 into v1 and c2 into v2 and c3 into v3, means in the similar manner wherever u1 u2 u3 is there, we are getting v1 v2 v3. and this is a scalar. Okay, so hence we show that as u1 u2 u3 span v, and v1 v2 v3 also it will span the v. Okay, the similarly this similar kind of problem here, he says that u1 u2 u3 are linearly independent. Okay, the vector space is v. In that case, u1 u2 v3 are linearly independent in v. So prove that the vectors containing u1 u2 u3 will also be the linear independent, means u1 plus u2 u2 plus u3 and u3 also linearly independent. Okay, the similarly as above, we can say that c1 is equal to u1 plus u2 and c2 into u2 plus u3 and c3 u3 is equal to 0. And if you do the cross multiplication and take the common things, then you will get c1 u1 plus c1 plus u2 into u2 and c1 plus c3 c2 plus c3 into u3. Okay, so hence he has given that u1 u2 u3 are linearly independent. We can say that c1 c1 plus c2 and c2 plus c3, these combinations individually equal to 0. So as these values are 0, then hence we say that u1 plus u2 u2 plus u3 and u3 is a linearly independent, because we know that if the values of c1 c2 c3 or x1 x2 x3 is all are 0, then the system we call as a linearly independent. Okay, so as it u1 u2 u3 are there, these three are 0. As 3 are 0, we call that the other function, that is u1 plus u2 u2 plus u3 and u3, okay, is also linearly independent here. Okay, then the main the one more main important the concept here, so fundamental four subspaces. Okay, so we call that, so here basically there are four fundamental subspaces. Okay, those are, so one we call as column space, null space. Okay, next we call as left null space, and one more we call as a row space. Okay, so all four are the basic fundamental subspaces. In that case, so already we know that what we mean by column space. Okay, so column space is nothing but, so it is a set of linear combination of the column vectors. Okay, the column space is nothing but is a set of or linear combination of its column vectors. Okay, so as we know, if this is a matrix like A is equal to this matrix, then column space of A is equal to alpha 1 into first column, alpha 2 into second column, and alpha 3 third column, so like that, so alpha n into the nth column, so that we call as C of A. Okay, the similarly, okay, so even the C of A we can call as range of matrix, not the rank, range of matrix. Okay, the next one, the next subspace, column space is the first one. The next subspace we call as a null space. So null space, we know that if it satisfies Ax equal to 0. Okay, so if null space having 0 vector, then we call as, means then we call as that system is a null space. Okay, or we can tell that there are many ways are there, or we can call that c1 equal to 0, c2 equal to 0 and c3 equal to 0, then we call as linearly independent. Okay, and if determinant is not 0, then also we call as linearly independent. Okay, so basically the null space is nothing but the set of solutions in a linear system if the system is like Ax equal to 0. Okay, then we know that, means what is a dimension? So dimension is nothing but the number of vectors in a basis. Okay, we will calculate the basis. How to calculate the basis? Okay, there will be a matrix, you will equate to some unknown values like b is replaced with, okay, means b vector basically, so b1 b2 b3, so that we will calculate the values in terms of the b1 b2 b3 we will calculate. So then that we call as the dimensions, the number of vectors in the basis, that we call as dimension of b. Okay, so now we see that the two spaces, column space and null space. Okay, the next two, okay, then okay, the before that, the dimension of column space, the dimension of column space is nothing but rank of a matrix, but the dimension of null space is nothing but n minus r. So n is nothing but number of columns. Okay, so the general notation m into n. If you take any matrix, we call that m into n. So m is nothing but rows and n is nothing but columns. Okay, so now the dimension of null space n minus r, dimension of column space is r, that is rank of matrix, and dimension of column space plus null space is equal to n. Okay, similarly dimension of column space and that's what the null space we call as the n, that is number of variables. Okay, the next one, the third subspace we call as row space of a. So row space of a is nothing but it is a column space of a raised to t means the transpose matrix of column space. Okay, the transpose matrix of column space we call as the row space of a. Okay, the row space of a we can represent as alpha 1 into row of a, alpha 2 into row of a, and row 2 of a, and alpha 3 into row 3 of a. Means the column space how we had given alpha 1 into, okay, column space we have given as alpha 1 and column 1. Okay, so alpha 2 column 2. So similarly here alpha 1 row 1 of a, alpha 2 row 2 of a. So transpose of that. Okay, the column if it is there it will become row, so that one. So then because of that he has given here the row space of a is equal to column space of a transpose. The last one, left null space of a. So that is nothing but the transpose matrix of null space. Means whatever the null space we will calculate, transpose of that we call as a left null space of a. Okay, so these are the four fundamental subspaces which will be indicated with notation C of a, n of a, C of a transpose, and n of a transpose. Okay, these are four fundamental subspaces. Okay, so here the rank of matrix. Okay, the rank of matrix, okay, the rank of matrix we can say that dimension of row or column space of a. Okay, the dimension of row or the column space of a matrix we call as the rank of matrix. So if the matrix is like this, then we say that the determinant of a is not 0. The determinant of a is not 0, then it is linearly independent. But what is the rank of matrix? The rank of matrix is nothing but either we call as number of pivot elements. So as we say that these are the pivot elements, okay, or number of variables. Okay, the number of pivot elements here in this is 3. Okay, so r is equal to, so rank is 3 here. Okay, so now find the null space. So now we know that what is, how to calculate the rank here and how to calculate the dimensions of these subspaces. Okay, so all those things. So now we can go for the solving the different the problems with respect to the null space, column space, and means basically the four fundamental subspaces.